So 6.3 part 2, we're still looking at graphing sine and cosine. Still looking at just individual transformations, I think, for now. Tomorrow, we're going to start looking at what happens when we put them all together. So that's when we have to make sure we follow the order that we're supposed to do transformations in. But I've been kind of telling you that as we go. I use the letter, anybody remember what letter I used with phase shifts? Well, vertical shift I used D. Phase shift I used A, because phase shift was the first one. Vertical shift is the fourth one. Now we're going to learn the second and third ones today. So the first one we're going to look at is what's called the vertical stretch. And that affects the amplitude. Okay, so the amplitude, if you just kind of want to see what it is visually, it's the distance from like the center of the wave to the top, or the center to the bottom. It should be symmetrical. And the amplitude, another word for that, is the height of the wave. Since amplitude is a height, what kind of number does height always have to be?
Positive.
Right. So if I ever ask you about the amplitude of a function, you should always be giving me a positive number. All right. So any questions on what amplitude is? Yeah.
So even when describing how far it dips down, you'd still use a positive number?
Yeah, because it should be symmetrical to how far it goes up. And it's the distance from the center line measured to here.
Right.
So anytime you're measuring a distance, it's always measured as a positive number, no matter which way you measure. Yeah. Okay, so yesterday everything that we did was inside the parentheses. Inside the parentheses is all your horizontal. Outside is vertical. When we're doing an amplitude change, that's going to stretch and compress the graph vertically. Whenever we do a stretch, is that when we have multiplication or the addition or subtraction? That's always multiplication. The difference today is the multiplication. That's the difference. It's multiplication. It's not addition or subtraction. That's what we did yesterday. And not only is this one multiplication, but it's multiplication in front. Okay? It's not multiplication next to the x. That would be inside the argument. This is in front. And I use the letter C, because when we do all the transformations, it's the third one that you deal with. In a minute, I'm going to give you some problems, and I'm going to ask you for the amplitude. Anytime that I ask you for the amplitude, you have to make sure you give me a positive number. Okay? If you're graphing, then you use whatever number is in front. So if you have this, and you were graphing -4 sine x, you absolutely have to take that negative into account. The negative has no effect on the amplitude, but it does do something to the graph. Does anybody remember what a negative?
Reflection.
It causes a reflection. So reflections don't affect the amplitude, but they do affect the picture of the graph. Right? And if you're not sure why they don't affect the amplitude, if that was your original, and you put a negative in front, it would look like this. It still goes as high and low as it did before. It just flipped. Okay? So negative, very important when you do the graph. Not important when I ask you for the amplitude. And I said that earlier, amplitude is always positive. That's my graph, and I take it and do something like this. Which axis is that stretching on?
The y-axis.
Right, stretching on the y-axis. So you can stretch or you can compress along the y-axis. And when I played the sound, what was the difference between a sound like that and a sound like that?
Volume.
That's volume, right? That's amplitude. So when you do these kinds of problems, there's a question I can ask you, which doesn't require a table, doesn't require a graph. The question is just find the amplitude. So the amplitude is the absolute value of the number in front. Okay, let's do this one. Y equals 3 cosine x. Okay. What would be the amplitude of 3 cosine x?
3.
Yeah, it would just be 3. All right. How about this one? 4/3 sine x plus pi over 2 plus 6.
4/3.
4/3. There's a lot of other things happening there. A lot of other things that do not make a difference for the amplitude. Shifting something left and right doesn't change how tall it is. Moving something up or down doesn't change how tall it is. It changes how high it goes. But there's a difference between how high something goes and how tall it is from, or how far it goes off of that center line, right? Shifting this up, if I go like this, that didn't change the amplitude at all. It still is the same distance from the center line when you shift it up and down. So any questions why it's 4/3? So those other numbers don't matter. How about this one? -2 sine x. Yep, the amplitude there is 2. What if I did negative? Actually, I don't want to do that. What if I put a +3 on it? The amplitude is still 2. That +3 didn't affect anything. What if I get rid of the negative? The amplitude is still 2. Changes the picture when I get rid of the negative, but it does not change the amplitude. Okay. Any question on that one?
Can I just go fill this? Do I have to send that to you?
Yeah, just sign out.
Okay.
What's so if we're stretching and compressing vertically, what part of the coordinate is going to get changed?
Y.
The y, yes. So if the y is going to change, that means the x's stay the same. And most people like when the x's stay the same because now you do not have to work with the 0, pi over 2. You don't have to work with any of them. So for all amplitude changes today, the x's are 0, pi over 2, pi, 3 pi over 2, 2 pi. And where did I get those from? I got them from the original table from yesterday. Okay, so any questions why the x's are staying the same when you stretch or compress vertically?
Yeah, how does that work?
So if I
so
just
it's
take,
just changing, but the points on the line are.
yeah, so if I take, let's just take a graph. Let's take, let's take this one. All right, and let's say I draw a wave like this. So here, here, here. Did I do that? That's okay. Now, if you take that wave and you stretch it vertically, just kind of watch this point up here. Can I stretch? Oh, I can't stretch it in both directions at the same time. That's what an amplitude change does. It stretches it up and down at the same time. But what I can do is this. Okay, and again, just watch the peak of that first one. So if I could stretch it both ways at the same time, it would do that. So this point right here, it didn't move left and right at all. All it did was move up. And then this point was up here, and it stretched down. So all that happens is the y values change. But every x value stays exactly the same.
Okay.
Any question on that? There's that one, and then back to that one. So all that's happening is the y value changes. Okay, so how do you change the y value? It's very easy. All you have to do is take the old y value and multiply by the number that you put in front. Notice here it doesn't say anything about absolute value. You just use the number the way it is, because if it's negative, that causes something important to happen. So multiply the old y values by c. And again, c is the number that's in front. So this one, you don't do the opposite. Okay? Vertical, you never do the opposite. If you put a 3 in front, that's going to stretch your graph 3 times bigger. If you put a 1/2 in front, that makes your graph half as tall. So it's what you see is pretty much what you get. Let's try an example. All right, so now we've studied 3 transformations. We've done phase shift, vertical stretch. Which transformation is that one? What is it?
Vertical stretch.
Yep, it is a vertical stretch. And why? Why is it a vertical stretch?
Because it's for multiplication, there's no inverse, so it's just 3 stretches in.
So it is multiplication. Anything else about it that makes it a vertical stretch?
Oh, it's in front of the cos.
Yes, so it's where it is. It's in front. In front is vertical. Yep, and it's multiplication. All right, so let's make our table. TJ, what column is going to stay the same?
It's going to be the x column.
And what are my original x's for cosine?
0. It's pi over 2. Pi. 3 pi over 2. And then 2 pi.
Yep, so those are your original x's. And Logan, can you give me my original y values for cosine?
1, 0, -1, 0, 1.
Yep. I didn't put those in the table because those are not the final answer. Those are the originals. All these y values are going to change. What am I going to do to all of them? Multiply them all by 3. So a vertical stretch in terms of the arithmetic is another very easy arithmetic one. All right. So Landon, what are my final y values?
3.
Yep.
0. -3. 0. 3.
There you go. And that's how you do your table for a vertical stretch. Any question on the table?
Not a question on 2, but you said that's a vertical stretch?
That is a vertical stretch, yes. Yep. And now we'll sketch it. Now, when I sketch it, you're not going to be able to tell it's a vertical stretch because I'm going to do this. I change the scale on my axes. And the reason I do that is because what if I had to stretch it like 35 times? I don't want to have to draw it 35 times as big. I'm probably going to run out of space. So what I do is I just change my scale. All right. So I change my scale there. X's, just use the standard values in the table. 0, pi over 2, 2 pi over 2, and 2 pi. You don't have to scale your y-axis that way. If you want to, make it look 3 times as big on paper, you could. All right, so we've got 0, 3. Next point, pi over 2, we're at 0. And then pi, we're going to be at -3. Back to 0, and then finish at 3. And when I sketch that, should it come to a point? No. It's a wave, so it's just try to make it look as curved as you can. That's okay. And there's your graph. And that's been stretched 3 times as tall. Now, if I did have to sketch it 35 times as tall, I would use that exact same picture. I just go like that. Now it's 35 times as tall. Okay. Any question on the sketch? Okay, so that was a stretch. How about this one? 1/2 sine x. What's going to happen here? It's going to stretch. Yeah, it's going to still be vertical, but it's not going to stretch. It's going to compress this time, right? Because you put a number in front, that's a fraction. It's smaller than 1. All right. So let's make our table. Nick, what column here stays the same when you do a vertical stretch or compress it? Yep, x stays the same. And Ethan, what are my x values for sine?
For sine, 0, 1, 0, 8, 1, 0.
Those are my y values.
Oh, sorry.
Yeah, we do need those, so I'll put those down.
0, pi, 2 over 2, pi, 3 pi over 2, 2 pi.
All right, so we got the x's, we got the y's. I know the y's are going to change, so I didn't put them in the table. How do I change all those y's? I'm going to multiply them by a half. Or instead of multiplying by a half, that's the same as what else? Dividing by 2. We're going to think about that next when we do the last transformation. But that's the same as dividing by 2. All right. So Riley, what are going to be my my final y values?
1/2, actually no, 0, 0.5, 0, negative 0.5, 0.
Yep. And that's your table for a vertical compression. Any questions on that table? All right. And now the sketch. Well, the sketch is going to look exactly the same as every sine function that we always draw. I'm just going to change my scale. So let's go 0, half, negative a half. And do your x's just like we did the last one. Okay, and we're at 0, 1/2, 0, negative a half, 0. So 0, half, 0, negative a half, back to 0. All right, now just make your sketch. No, it's not perfect, but it's okay. It's good enough. All right, any question on the sketch? Okay, so we did the compression. Did stretch. The only thing left, which we kind of already mentioned, is when you put a negative in front. Just so we know what we're going to kind of expect here. What does the negative in front do?
Is flips it across the x-axis.
It does flip it. How does it flip it? Oh wait, which axis did you say again?
X.
Yeah, it is the x. Yeah, it reflects it over the x-axis. Yep. So normally when you graph cosine, it looks like that. Well, that's going to flip. So instead of looking like more like a valley, it's going to look more like a hill kind of thing. All right, so let's do that one, and then we'll do our last transformation. X's stay the same. Hopefully you're kind of starting to remember what these x's are now because we use them a lot. Okay. And Jacob, what are my original y values for cosine?
0, 1, 0, negative 1, 0.
Those are for sine.
Oh. 1 0 negative 1 0 1.
Yeah. And what's going to happen to all those y values to get the new ones? What do you mean flip them?
Like change the sign.
Yeah, just change the sign of all of them. So this becomes negative 1, 0, 1, 0, negative 1. So the ones that were zeros don't change. But everything else changes sign. Alright, and make our sketch. Technically, you don't need to label the y-axis because you are going to go by ones on this one. So if you didn't label it, that would be okay. But definitely label your x's. All right, so start at negative 1, up to 0, up to 1, back to 0, and finish at negative 1. Okay, just always remember, it's a wave. It's nothing that comes to a point. So try to just give it that wave. Just like that. Oh, that's an exclamation point. Not bool. And I was written kind of messy. All right, any question on the wave there? All right. That's it. All right, so that's stretching and compressing vertically, and that's where you hear the change in the volume. Like I said, the change in the pitch, the low frequency one, that's really cool. So maybe someday I'll be able to show you. But you can hear the high frequency one, and that's a good test to see what frequencies you can hear, because eventually the higher ones, they just kind of stop working. You can't hear them anymore. And even for some people in here, when I got to like 19,000, they just couldn't hear anymore. Got too high pitch. But sometimes you can tell it's playing, because like if I play around with it, like play the different sounds a lot, like for multiple classes, sometimes my ear starts feeling like really warm. And I don't know if it's because things are vibrating. When things vibrate, they get warmer. So it's probably not a great idea to keep doing it. But even though I can't hear it, I can tell that something's happening because it keeps playing, and I get a headache after a while. So it's probably not good to play high frequency, loud sound, loud volume all the time. All right, so we talked yesterday about the amount that you have to travel along the graph before it starts to repeat. And that amount that you have to travel from here over to here was 2 pi units. If you travel more than that, you're going to be repeating the values you already saw before. Well, when we do a period change, we can stretch or compress that distance. You may have to travel further than 2 pi in order to see a full sketch, like if I did something like this. Okay, this type of graph has been stretched quite a bit. You're still seeing, a full cycle, but I could stretch it even more. And now I don't think you'll see a full cycle because I've stretched it out too much. It would have to get back down to here for you to see a full cycle. So in that case, we want to figure out, I stretched it, so what's the new cycle length? It's not 2 pi. This one would actually be 8 pi, would be times 4. So yeah, this one would be 8 pi because I actually stretched it 4 times as much. Now, notice that may not make sense right away. I put in a small number, but a small number stretched it bigger. That's because this is the opposite. Small numbers make the graph bigger. What do you think is going to happen if I put in a big number? A big number makes it smaller. So instead of having to travel all the way to 2 pi before you see a full cycle, if you put a 4 in front, which I think that's what I put, a 4 compresses it 4 times as much. And that changes, what did that change about the sound?
Pitch.
It changed the pitch. Yep, changed the pitch. Okay, so that's what we're going to be changing. We're going to be changing the length of the cycle before it repeats itself. And what is that in degrees? It's 2 pi radians, but that's equivalent. It's equivalent to 360. Yep. Okay. It's a stretch. We know stretching is always multiplication. What's the difference between this is multiplication, but so was the last one? What's the difference? Yeah.
It's in the parentheses.
Right. It's inside the function with the x. So that's the big question. Is it inside the argument or is it outside the argument? This is inside. So inside is horizontal, multiplication, stretch or compression. Now, b can be any number except 0. Because if b was 0, that wipes everything out. Then it's gone. But we're going to focus specifically on when b is a positive. All that would happen if it was a negative is it would do a reflection. But it wouldn't reflect over the x. It would be over the y. Right, but we're going to focus on when b is positive. So which axis is it stretching or compressing on? Horizontal, which is the x. Yes. So this is stretching or compressing along the x-axis. The other thing I didn't mention, but it will be important, I used B for the letter for a horizontal stretch.
It stretches or compresses graph.
It stretches or compresses graph. Yes, graph. Oh. Never happened. Graph. So the reason I use the B is because this is going to be the second transformation when you have multiple ones that you always deal with. Right? So now you know the order of all of them. Phase shift comes first. Period change or horizontal stretch comes second. Vertical stretch, that used the letter C. That was the third one. And vertical shift used D. That's the fourth one. And yes, it does make a difference the order you do that. It's like penalties. So we'll talk more about that tomorrow. If you plug in a number that's big, the graph gets smaller. The bigger the number, the smaller it gets. Eventually, if you compress it too much, then you don't even really have a meaningful picture because you can't even see what's going on there.
A bunch of guys.
Yeah. It looks like a bunch of what?
Looks like people, like upside down.
Oh, people, yeah. So there's kind of a limit to how much the calculator can show you. I mean, maybe around, for that window, maybe 10. It's kind of still okay. But the resolution is a little rough, so it doesn't look as smooth, and it starts to look like it's coming to a point. You could fix that by zooming in, and then you would see it's a smooth curve. All right, so greater than 1, you're going to get compression. The smaller you make the number, the more stretch the graph gets. Okay, so if you stretch and compress horizontally, what part of the coordinate is going to change? The x. Yep. Actually, I think I jumped ahead. That's going to be the next thing I mention. But yeah, we'll mention that in a second. So I told you earlier, we want to be able to find the new period. Okay, what's the standard period that we've done all week?
2 pi.
We've always been doing 2 pi. If you want to calculate the new period, that's the formula to find it. It's 2 pi divided by b. Why do they use the letter T for period? I'm not sure. But this matches what's in our book. So just to be clear, the period is not b. The period is 2 pi divided by b. That's how you find the period. And that works for sine. It actually works for 4 different trig functions. It works for sine and cosine. It also works when we study secant and cosecant. It does not work for tangent and cotangent. You've got to do something a little different to adjust it to tangent and cotangent. We'll talk about that next week. Okay, so no table for this particular question, no sketch. All I want to know is the period. So the first thing you want to always write down is 2 pi divided by, and then identify what b is. Okay. What's b in this case? 2. So what's the period of this? Pi. Compared to the original period, is that a stretch or a compression? That's a compression. The original period was 2 pi. This is 1 pi. It got smaller. How much smaller? Half as big. Half as big. Let's try to find the period of this one. Always start out t equals 2 pi, and now identify what b is. What's b in this case?
1/3.
Yep, b is 1/3. That's going to be 6 pi. Yeah, think of 2 divided by 1/3 becomes 2 times 3. I told you we kind of talk about that. When you divide by a number, it's the same as multiplying by the reciprocal. Yep. So it's 2 times 3, which is 6 pi. That's a stretch. How much of a stretch is that compared to 2 pi?
3 times.
Yep. It's a horizontal stretch, 3 times as much. All right. How about this one? What goes in the top? 2 pi. And what goes in the bottom? So what's the period of this one? 2. Yeah. 2 radians. That's the period. So you have to travel 2 radians before you see a repeat. Alright, and let's try one more. Okay, you could answer this part without even looking at it. What goes in the top of the formula to find the period? Okay, 2 pi. Now you need to know what number you're looking at. What goes in the bottom? 3. Vertical stretch doesn't do anything to affect the horizontal. Neither does a vertical shift. So based on that, what if I did this? What would be the period now? Still be the same thing. Shifting up and down does not affect horizontal stretching. They're all separate.
What was the equation for B?
For T,
B, just for like the one up above.
B is given to you. It's always what's in front of the X.
No, like we had 4 examples. So one labeled B. Like if you look at
Oh, example B.
yeah, that one.
Oh, not the B in the
No.
formula. Okay, example B.
I just didn't get that one.
Yeah. Okay. Any question on finding the period? All right. So the last thing is making a sketch. So I think we already said what stays the same. We kind of jumped ahead. What stays the same when you're stretching and compressing horizontally? The y's. Unfortunately, the y's are the easy ones to work with. And you don't get to work with them this time. They stay the same. So you're going to copy down the 1s and 0s from the original table. And now we have to find the new x's. So to find the new x's, we're going to take all the original x's and divide them by b. That's how you find the new x's.
Yep, scroll back.
Now, if b is a fraction, I'm probably not going to want to divide by a fraction. So instead, I'm going to multiply by the reciprocal. Yep. If b is like 2, well, fine, I can just divide by 2. But if b is 1/3, I don't really want to divide by 1/3. I'd rather think about that as timesing by 3. So, in a sense, maybe not as bad as a phase shift because you do not have to worry about common denominators whenever you're dividing. So, common denominators aren't a thing you need to think about. Okay. Any question on the 2 steps? All right, so we'll try maybe 1 or 2 examples of horizontal stretching compression, period change, and then that'll be it. All right, so we have sine 1/2 x. Okay, first of all, where's the number? Inside or outside? Inside, that means horizontal. And is it addition or multiplication? Multiplication means stretch. So it's horizontal, stretch. Okay, when we do a horizontal stretch, what stays the same? The y's. What are my y values for sine? Yep.
0, 1, 0, -1, 0.
Okay. Those are my y's. Okay. Off to the side, I'm going to put my original x's. Can somebody else remind me? What are my original x's for sine?
0.
Yep.
Pi over 2. Pi. 3 pi over 2. 2 pi.
2 pi. And now the directions say divide by b. Okay. What's b in this case? B is 1/2. So I need to divide all of those by 1/2, which really means to do what? Right. I'm just going to say multiply by 2, because that's an easier way to think about it when b is a fraction. Right? So instead of dividing by 1/2, we're going to multiply by 2. And we're going to get 2. What's pi over 2 times 2? Just pi. Well, it's 0. Yeah, 0 times 2 is 0. Sorry about that. All right. What's pi times 2? 2 pi. What's 3 pi over 2 times 2? 3 pi. 3 pi. And 2 pi times 2? 4 pi. Are those x's all evenly spaced? Yeah. They're all 180 degrees apart. That's how much pi is. 180. Okay. So use those x's for your labels. And for the y's, again, because you're going to go by ones, you don't have to label it. That's up to you. I would go by ones, though. Yeah, just like when I did the vertical stretching and compressing, you're not going to notice. How come this graph isn't going to look stretched or compressed? Yeah?
Is it because the y's are going to change? As in, like, it's just 1 and -1? It's not.
Well, the x's are changing, but how come you're not going to see the change in my picture? All the x's are different. Yeah?
Because of the way you're scaling it?
I changed my scale, yeah. Because normally this would have been pi over 2, pi, 3 pi over 2, 2 pi. So this graph is going to look just like the original because I changed my scale. All right, so we got 0, 1, 0, -1, and 0. But we should know, did this graph really stretch or compress, even though it doesn't look it because of my scale? It's stretched. Right? Normally, the graph would have done an entire wave, something more like this, between 0 and 2 pi. Now you got to go to 4 pi before you see a full cycle. So you got to go twice as far because it's stretched twice as much. Okay. Any question on the 2 steps? Yeah. So we'll try one more stretch or compression, and then that'll be it. Let's do this one. Cosine pi over 3x. Again, look for where the number is and look for what operation. Where is inside? What operation? Multiplication. That's a horizontal shift. So, y's stay the same. Jacob, what are my original x's for cosine?
0, 2, or pi over 2, pi, 3 pi over 2.
Perfect. And now we need to divide them by b. What's b in this case?
3.
Pi over 3. So I don't really want to think about dividing by pi over 3. I want to think about multiplying by 3 over pi. So multiply these all by 3 over pi. Right, we'll start with the first one. What's 0? Yeah, 0 times 3 over pi is 0. Now here, the pi's cancel. So what's 3 divided by 2? 3 over 2. Yeah, you just put 1.5. How about the next one? 3. Pi's cancel. 3. Pi's cancel. And you get 9 over 2, which is 4.5. And here the pi's cancel. So you get 6. Are my x's evenly spaced? Yeah, if they're not, you did something wrong. They have to. And this time, when I number, I would just go by ones. I mean, you could. Well, you know what? Let's do it the way we've always done it. I guess you could scale it by 1.5. That's the way we've always done it. And what's the highest y value that I need? 1, and the lowest? And now graph your points. 1.5, 0, 4.5. We're at 0 and 6. Back at 1. And draw your sketch. That was not a good one. That wasn't that great. You get it. Any questions on it? All right. So that's the horizontal stretching, compressing, and the vertical. So tomorrow we'll put them all together, and we will use the calculators more tomorrow as well. So the homework, pretty similar to what it was last night. Make sure you show the graph. So show your sketch. And we'll take a look at that first thing. Come on.